Welcome to the CD-LACOM video series number 2. In this video, we will review setting up and positioning the PV loop catheter for optimal data acquisition. We will start with the PV loop catheter on the table. First, the pressure sensor should be wrapped in wetted gauze for a minimum of 15 seconds. Next, we will connect the PV loop catheter to the volume and pressure interface cables, which should both be connected to their appropriate Inca modules. It's recommended to first connect the PV catheter's volume connector with the volume interface cable. To make this connection, align one end screw with the solid line on the dial to the other end solid line on the dial and screw so that there is a straight line across the connection. Screw, solid line, screw. Once this orientation has been achieved, push the dials together laterally and twist a quarter turn to lock in place. The second connection to be made is the PV catheter's pressure connector with the pressure interface cable. This is a male-female connection that can only be made in one orientation. Once identified, push the two connections together so that they are flush. Upon making the pressure connection, BiV Conduct NT will prompt the user to calibrate the pressure signal. Select Calibrate only after ensuring that the catheter is outside the body, the pressure sensor has been wrapped in wetted gauze for a minimum of 15 seconds, and the pressure sensor is untouched. Because of the electronic nature of CD-LACOM's pressure sensor, one does not need to calibrate the pressure signal relative to patient height or orientation, as is typical with a fluid-based pressure system. After the automatic pressure calibration is complete, rescale using F9 or the rescale button in the toolbar. The pressure signal will change from red to blue by default, confirming that this is a calibrated and zeroed signal. Next, the PV catheter should be delivered to the appropriate ventricle such that the pigtail is at the ventricular apex and the catheter shaft is centered along the ventricular long axis. Initially, fluoroscopy or another imaging-based tool should be used to determine catheter positioning. Then, we will optimize catheter positioning through the BiV Conduct NT interface by going to View Segmental Loops. This view plots the single pressure signal against each of the 7 ventricular volume segments to provide a series of PV loops called segmental loops, which help determine the PV loop catheter positioning. To orient ourselves, note that segment 1 is collected closest to the apex of the ventricle, while segment 7 is collected closest to the base of the ventricle. While in segmental loops view, we will first determine the depth of the PV loop catheter by looking at segment 1's minimum y-axis value on the left of the screen. Here, this minimum value is indicated as 12.79 milliliters. This minimum value is affected by varying ventricles, ventricular sizes, and ventricular geometries, but typically this value should be around 15 milliliters or less to indicate the PV catheter is delivered all the way to the apex. If this value is not 15 milliliters or less, and there is space to advance the PV catheter's pigtail further towards the apex, it is recommended to do so. For the operator, please think of the apex as an anchor for the pigtail, as we don't want the PV loop catheter moving during the procedure. If the catheter doesn't move, it can appropriately compare baseline hemodynamics to that throughout the intervention. Next, we will determine the centeredness of the PV loop catheter by analyzing the segmental loops themselves. One should expect to see counterclockwise PV loops that are rectangular in shape to indicate quality positioning. For RV PV loops, the loops may be more triangular in shape, but they should still be in a counterclockwise orientation. As a reference, recall that segment 1 is closest to the apex and the pressure sensor is located across segment 3. Thus, if a ventricular pressure signal is visible, as we see here in total volume PV loop and indices view, then one should expect to see a minimum of 3 counterclockwise and rectangular segments while in segmental loops view. This is the case for any PV loop study, regardless of LV or RV PV loop acquisition. If there are less than 3 counterclockwise and rectangular segmental loops, it's recommended that the operator reposition the PV loop catheter by either A, pulling back on the PV loop catheter and redelivering to the apex, or B, providing a quarter of a turn to help use the pigtail to center the catheter shaft along the ventricular long axis. To reiterate, The goal in optimizing the PV catheter's position is to achieve a minimum of 3 good segmental PV loops with stable signals. Please note that these segments do not need to be consecutive. Any 3 good segments can be used for accurate volumetric changes. If one does not see 3 good segmental loops, then this is an indication that the PV loop catheter needs to be repositioned. Data quality is directly related to catheter positioning, thus it's highly recommended to optimize PV catheter positioning before continuing with the intervention. After optimal PV loop catheter positioning has been achieved, we will remove any segments that are poor quality and/or not in the ventricle. These segments are indicated by a clockwise loop or a figure of 8 and typically should be removed in real time. To do so, go to Settings, Catheter, and remove any segments that you do not wish to have included in the total volume measurement. From here, white text will appear indicating segments not used in the total volume calculation. Finally, rescale using F9 or the rescale button in the toolbar to display the total volume signal on the screen. Please recall that the Inca system acts as a black box. Thus, inclusion or exclusion of any segments can be done offline in post-data processing. At this point, we have optimized catheter positioning, removed any unneeded volume segments, and are ready to begin data acquisition. Start by switching back to our monitoring view by selecting View, Total Volume PV Loop and Indices. Now, you're ready to begin recording PV Loop data.